Okay, the last component we defined in our previous lecture was capacitor. In particular, we talked about the LTI case, the linear primary capacitor. Now we will continue with the other component that's able to store electrical energy, that is inductor. Okay. Now, here is the general definition for inductor, and then we will concentrate on, once we give that general definition, we're going to be concentrating on the LTI inductor. Okay. Now, inductor is a two-terminal component whose magnetic flux, okay, indicated by the Greek letter phi, and current I satisfy a relation described by a curve on phi I flux current plane. Okay. Note that although this statement here tells us something very different than the statement that we use to describe a capacitor, qualitatively those two statements are very similar. Okay. In the sense that in defining the capacitor, instead of flux, we had a related charge, because capacitors are able to store charge, and instead of current, we had voltage. Okay. In capacitor, charge was related to voltage. Now, the inductor, flux is related to the current. Okay. This is the symbol that we use in our circuit drawings, this spring-like thing, okay, plus, minus, E, this is I, and this is the associated flux to our inductor. For example, okay, suppose that this is I, and this axis indicates flux, and the current and flux are related to one another, such that for a while it's staying here, and then if you further increase the current, flux stays constant, it saturates. Okay. Now, current and flux, they satisfy a relation, and then if you have such a component, that component belongs to the category of an inductor. Okay. Now, eventually, we want to relate the current to voltage, because in general, we want to be able to express everything in terms of voltage and current of our components. And for that, what we use Faraday's law, which relates the flux of a component or of an inductor to its voltage. Okay. Faraday's law. Okay. Vt, voltage, is related to equals the rate of change of flux of the phi t. Okay. And remember once again, capacitor. In capacitor, we had the case that charge is related to voltage, and then we want to be able to obtain a relation between voltage and current, and for that, what we use the definition of current. Okay, so that taking the charge, from charge we obtain the current by using the definition, which was I of t equals dqt over dt. And now that was the definition. Now we're using qualitatively a similar equation, but this time it's not a definition, but this is coming from nature itself. It's Faraday's law, and voltage is related to flux through that differential equation. Okay. So that's the general definition for inductor. In this course, we will almost always be interested in the LTI case. So let's therefore talk about the properties of an LTI inductor. LTI inductor. Okay. Not surprisingly, by an LTI inductor we mean the following: flux is always proportional to current. Okay, and that proportionality constant is called the inductance. Okay, LTI inductor I phi, and the relation is linear between flux and current, and here the slope of this line has a special name. It's called inductance. Okay. So phi of t equals L I of t. This is the current flux relation for linear time invariant inductor. Okay. Once again, for the capacitor, we have Q equals C capacitance times the voltage. Although those two equations, this equation and that equation, tells us very different things, but qualitatively, or they form, are identical. Okay. So L is called inductance. Okay. And it's measured in units called henries. Okay. Capital H. Remember that for capacitance, the unit that we used was farads. Now, for LTI inductor, using the linear flux current relation plus the Faraday's law, now we will get rid of the flux altogether, and we will relate voltage to current, or current to voltage for LTI inductor. So that's for the next question. What's the IV relation for an LTI inductor? Okay, so V of t equals here V t equals d over dt by t. We start from Faraday's law, and then we will replace phi of t with its current representation. That is d over dt L by t. And then L is constant, therefore we can take it outside differentiation, and we're left with L dit dt. Therefore, for an LTI inductor, voltage is proportional to the rate of change of current. Likewise, similarly for capacitor, current was proportional to the rate of change of voltage. Okay. V of t equals L dit dt. Okay, this is for LTI inductor. Now, if you want to put the current on the left-hand side, the equation becomes an integral equation. Equivalently, I of t equals initial current, then you integrate the voltage. 1 over L t0 to t v tau tau. Okay, that's another IV description of LTI inductor, another but equivalent to the differential equation description. Okay. Now let's also talk about power, and more importantly, the stored energy for an LTI inductor, and then we can summarize what we have seen for our LTI components altogether: LTI resistor, LTI capacitor, and LTI inductor. Okay. So power for an LTI inductor goes as follows. We start from the general definition of power of a two-terminal component, which is the product of voltage and current. V of t times I of t. And then we replace the voltage by its current description, LTI dt. So that gives us the IT dt times IT. Therefore, the power at any given time equals LIT times the IT dt. Okay. Then, by integrating power, we can obtain the stored energy. Stored energy, okay, for a passive LTI inductor reads as follows: W of t or E of t equals minus infinity to t p tau e tau. Okay, p is the power, and then that we can represent using this equation we obtained in terms of voltage. Excuse me, in terms of the current. I minus infinity I t L I I. And it's easy to integrate the integrand, and that immediately gives us 1/2 LIT squared, equal by definition I at minus infinity equals 0. Okay. So let's put that in a box because it's very important. Stored energy for an LTI inductor is proportional to square of the current passing through the inductor at that particular time. Okay. So that's more or less what we want to say about LTI inductor at this moment. Okay. Later on, when we start dealing with circuits that contain LTI inductor and LTI capacitor, we will review all these and we will add certain new things to our findings. But for now, this should be enough as an introduction. Okay. Now, let's summarize the properties of our LTI components, namely our major basic players in circuit theory: LTI resistor, LTI capacitor, and LTI inductor. Summary of LTI resistor, inductor, and capacitor properties. Okay. Let's put all those properties in a table so that it's easier to see and, more importantly, to compare what is what. So, so this column is for an LTI resistor with resistance, let's say R. This column is for an LTI capacitor with capacitance C, and the last column is for an LTI inductor with inductance L. This row is for algebraic equation that describes, in some sense, the property of the component. Here is the IV characteristic of the component, and here. Here is the energy stored at time t. Okay. So I want to make just a little modification. I want to put inductor here and resistor over there because of the space consideration. This is inductor L and this is resistor with resistance R. Okay. Now, algebraic equation. For an LTI resistor, the algebraic equation is given by the Ohm's law, okay, which is V of t is proportional to the current I of t, and that proportional to the constant we're calling the resistance. It's measured in ohms. For capacitor, the algebraic equation was charge is proportional, the charge stored is proportional to the voltage that appears across the terminals of the capacitor, and the proportional constant we called the capacitance, C. And for inductor, flux of the component is proportional to current passing through the component, and the proportional constant we call inductance. Okay. LIT. IV characteristics. Note that for LTI resistor, this algebraic equation is already in terms of voltage and current. Therefore, this is directly our IV characteristics. Okay, we have V of t equals R IT. Or if you want the current on the left hand side, you can write I of t equals 1 over R, or sometimes called G, the conductance, times the voltage, V of t. Now, for capacitor, the algebraic equation is in terms of charge and voltage. And now from that equation, we want to obtain a relation between current and voltage. And for that, what we use the definition of current, which is rate of change of charge. Using that definition, we can easily obtain I of t equals C dVt dt. So that's the IV relation for the capacitor. Or if you want to put the voltage on the left hand side, it's Vt equals V T0 plus 1 over C T0 to T I tau beta. That's the integral representation of IV characteristics. Okay. And then for LTI inductor, the algebraic equation is in terms of flux and current. And what we want is we want to obtain a relation between current and voltage. And for that, what we use Faraday's law, okay, which relates voltage to flux. Namely, voltage is the rate of change of flux of the component. And if you do that, and we did that, we obtained V of t equals L di t over dt. And if you want the current on the left hand side, you write it as an integral I t0 plus 1 over L t0 to t v tau beta. Okay. And energy stored at time t. Okay. Now, inductor and capacitor, they have this very important property. They can store energy. But as for resistor, it's not able to store energy. What happens with the energy that it absorbs from the circuit? It takes that energy, electrical energy, and it transforms it to another form of energy. It transforms it to heat, so it's lost. Well, I'm talking about the passive case, or positive. It's lost from the circuit. Okay. So therefore, for an LTI resistor, energy stored at time t is irrelevant because resistors are not able to store energy. Whereas capacitor inductor, they are able to store energy, and we obtained the following relation for capacitor. Stored energy at any given time, W of t or E of t, is directly proportional to the square of the voltage at that particular time. In particular, we have 1/2 CVT squared. And for inductor, we have an equation that has exactly the same form of this equation, where the capacitance is replaced by inductor and voltage square is replaced by the current square. So we have 1/2 LIT square. Okay. And this table here contains all the necessary terminal equation information and more, in fact, because we also apply energy regarding our 3 most important players, okay, or components in circuit theory. Okay, LTI, resistor, capacitor, and inductor. Okay. So, of course, we will have some other components. Okay, they're minor, but they are also important. We will define them soon, and we will redefine them as we go along. Okay, but mainly speaking, this table plus Kirchhoff's laws, KCL and KVL, is what we need in order to be able to solve and understand a circuit. Okay. Now, before defining so-called minor components that we will be dealing with, like dependent source or ideal transformer, let's give a very simple example of what we mean by solving a circuit. Okay. Now, this is the example where we solve our first circuit, okay, in this course. It's a very simple circuit and contains only sources, independent sources, and an LTI resistor. For now, circuits containing inductors and capacitors, those are called dynamic components. We'll start talking about such circuits toward the end of the semester. Okay. For a while, we'll be dealing only with circuits which can be represented through equations that do not contain differential equations or integral equations. Okay. Now, this is our circuit. E120 volts equals 6M. R1 equals 10 ohm. R2 equals 50 ohms. Plus minus V1 I1. Plus minus V2 I2. Okay. Now, this is a circuit with 2 independent sources. One of them is independent voltage source, and it's a constant source, it's a battery. The other is independent current source, which also is constant. This gives 6 amps in that direction, and this provides 120 volts with polarity plus minus, given here in the circle. And in this circuit, we have 2 LTI resistors. One of them is here, we call it R1, okay, whose resistance is 10 ohm, and the other resistor, second resistor, has resistance 50 ohms. Okay, and for this circuit, we'll ask find the currents and voltages of the resistors. Okay. And the current and the voltage of the resistors are labeled as, this is plus minus V1, and we obey passive sign convention, therefore this current is called I1. And for the second resistor, plus minus V2 is its voltage, and I2, again obeying passive sign convention, is given in that direction. Okay. Find the currents I1, I2, and voltages V1, V2 of the resistors. And B, verify that total generated power in the circuit equals, because it must, equals total dissipated power. Now, later on we will develop very powerful systematic tools, okay, for systematic approaches to solve a general circuit, okay. But at this point, since we don't have any systematic tools, what we will do is we'll write down everything that we can write down, and that everything will be coming from determinant equations, and also KCL and KVL. And then by looking at those equations, we will try to figure out the currents and the voltages. And in this case, it won't be really messy because this is quite a simple topology, quite a simple circuit with only 4 components. Okay? And then once we have the currents and voltages, once we solve the circuit, we will compute the powers, okay, for each component, and verify that total generated power equals total dissipated power. But for now, let's concentrate on solving the circuit. Okay. Here is a way to approach the problem. Now let me do some labeling first. Before, let's write what we can write. Okay, first of all, we know that this is an LTI resistor, therefore voltage and current are related to one another through Ohm's law. Okay, V equals R. So let's begin by writing those. Solution A. Ohm's law says that V1 equals R1, I1. R1 is given to be 10 ohms, therefore that equals 10 I1. V1 equals 10 I1. Likewise, V2 equals R2, I2. R2 is given 50 ohms, therefore we have 50 I2. Okay. So we have 4 unknowns, and we have now 2 equations already. V1 equals 10 I1 and V2 equals 50 I2. Okay. So we need 2 more equations, and those 2 equations will be coming from, one from KCL, the other from KVL. Let's start from the KCL. Let's write KCL at this node. Let's call that node A. Okay. KCL at node A. Now, if you imagine a closed surface around that node, and we can easily write KCL, which says sum of incoming currents must equal sum of outgoing currents for any closed surface. So we can write as follows. We can imagine all the currents as incoming, let's say, and no outgoing current. Therefore, sum of incoming currents equals 0. So this I1 is incoming, okay? I1, and then we have, this is I2 outgoing, but we want to consider everything incoming. Okay, so minus I2 would be incoming. And finally, this I, which is 6 amps, is also incoming. Okay, so KCL says that I1 minus I2 plus I must equal 0. Therefore, I1 minus I2 equals, I is given, okay, minus 6. Let's call this equation. And then let's also make use of KVL at loop 1. Okay? To be able to make use of KVL, all you need is a loop, a closed path. And let's choose our closed path to be this one, which I'm calling loop 1. Now this loop is associated to 3 voltages, V1, V2, and here 120 volts E. Some of those 3 voltages, of course, respecting the polarities, must be 0. So let's do that. So we're going in clockwise direction. The first voltage is V1 plus minus, second voltage is V2 plus minus, so everything should be plus minus so that we can write the equation properly. And finally we have plus minus this voltage, but this voltage is given as plus minus plus, but it's only a minor difficulty. We can make this minus plus plus minus by negating this 120 volts. Okay. So therefore we have V1 plus minus plus V2, and finally plus minus 120 must equal 0. Minus E equals 0. Okay, E is given to be 120 volts. Therefore, we have V1 plus V2 equals 120. Okay. Now we can express V1 and V2 in terms of I1 and I2 using Ohm's law. Therefore, this can be written as 10 I1 plus 50 I2 equals 120. So let's call this equation 2. And now using equation 1 and equation 2, we can solve for I1 and I2. Once you have I1 and I2, you can obtain V1 and V2 easily, and then part A will be solved. Now, combining equation 1 and equation 2 as we obtained previously, we can solve and obtain I1 equals minus 3 amps and I2 equals plus 3 amps. Okay. And then once you have I1 and I2, you can easily compute V1 and V2 using Ohm's law. That immediately gives us V1 equals minus 30 volts and V2 equals 150 volts. Okay. And part A is complete. Now what we will do is we will compute for each of our 4 components the associated power. Of course, obeying passive sign convention, and by doing that, we will be able to determine whether the power is absorbed by the component or delivered by the component. Okay. B. For the voltage source, okay. So let this resistor be our first component, this is our second component, and voltage source third component, and the current source, fourth component. Third component, its voltage is 120 volts with polarity plus minus. We want to obey passive sign convention, therefore the current that be assigned to it must be in that direction, entering from the positive label terminal, leaving from the negative label terminal. Okay, we're calling it I3. And what's I3? If you write KCL at this node, all the currents are leaving, outgoing. I1 plus I3 must be 0. Therefore, I3 must equal minus I1 by KCL. Okay. So I3 equals minus I1, and I1 is minus 3. Therefore, I3 is 3 amps. Therefore, the power of the voltage source P sub E, that's noted in such a way, equals the product of voltage and current. The voltage is 120 volts, the current I3 we computed to be 3 amps, therefore 3 times 120, that's 360 watts. plus 360 watts. Okay, so that means, since we obey passive sign convention, that means even though this is an independent source, meaning that it's capable of delivering power, in this configuration, it's absorbing power from the circuit. Okay, so it's absorbing power from the circuit. How about the current source? So this was our third component, and finally, current source is our fourth component. Its current is 6 amps in that direction, and its voltage, because we want to obey the passive sign convention, voltage, the polarity should be chosen such that this is plus, this is minus. Okay, this is V4. Therefore, the current enters from the positive label terminal and leaves from the negative label terminal. If you can figure out V4, then V4 times I, the current, will give us the power of the independent current source. Okay, so therefore let's compute V4. Okay, now V4 equals minus V2, and that can be easily obtained by using KVL in this loop, where this guy and that guy are connected. Okay, so if you consider this loop, you have V4 plus V2 equals 0, therefore V4 must be minus V2. And we know what V2 is. It's 150 volts. Therefore, that's minus 150 volts. Then the power, okay, we denote by P sub I equals the product of voltage and current. Voltage, we now know V4 is minus 50, minus 150, and the current is 6. The product gives us minus 900 volts. 6 times minus 150, that gives us minus 900 watts. Because we respected passive sign convention and the sign turned out to be negative, we now easily interpret what that means. It means that this source is delivering power, electrical energy, to the circuit, to the rest of the circuit. So it's delivered. And finally, let's quickly compute the powers of the resistors. Okay, for first resistor, let's call it PR1. We have I1 times V1. And that equals 90 watts. And R2 for the second resistor, the power is I2 V2, or equivalently we can use the formula obtained R times I square. Okay, I2 square. That gives us 450 watts. Both are positive, so that means those resistors are absorbing power. Okay. Now, since we have all the powers, we can return to the statement of the second part. It says that verify total generated power equals total dissipated power. So this means this verification consists of the following procedure. You look at the powers, you sum all the powers with positive sign, and you sum all the powers with negative sign, and you compare those two magnitudes, and they must always be equal. Okay. So let's do that finally. Hence, power generated equals, you sum all the negative powers. We have only one negative power, and that's minus 900 watts for the current source. So what we have is minus 900. We're now talking about magnitudes only. So what we have is 900 watts of power that's being delivered or that's being generated. Okay. And this is by independent current source. And now compute power absorbed or power dissipated. Okay. And that equals sum of all the powers with positive sign. Here we have 360 for the voltage source, plus 90 for the first resistor, and finally 450 with this for the second resistor, and that gives us 900 watts. Okay. Therefore, power generated equals power absorbed. Okay. Now that this is not a coincidence, this must always be so. And why that is, we'll see soon enough. Once we see, once we study, once we discover the so-called Telegrams theorem. Okay. Okay. Now let's wrap up this lecture by introducing some of our minor components, okay, and then our list of components will be complete. Namely, we'll talk about so-called dependent sources and ideal transform. Okay, this is our next component, or next class of components called dependent sources. Let's concentrate on the linear case. The nonlinear case is easy to understand, at least from the definition point of view. A linear dependent source has terminal characteristics controlled by a current or a voltage of some other branch in the circuit. Okay. There are four kinds. Okay. First is called voltage controlled voltage source. Okay. Controlled voltage source. The short name for this is VC VS. Okay. And here is the description. Remember that independent sources we represented by a circle, and dependent sources are represented by this diamond shape. Now, it's a diamond shape, that means it's a dependent source, and this is a voltage source, dependent voltage source. Therefore, here we have the polarity plus minus. Okay. Then here we have some constant times V1. And then that's given, and what this means is the voltage that appears across the terminals here, plus minus, is mu times V1. Now the question is, what's V1? What's V1 must also be given. It's a voltage of some component or some branch inside the circuit. Okay. Okay. Suppose that this represents another part of the circuit, and that part generates some voltage, and that voltage somehow is communicated to this device, and this device produces voltage that's proportional to that first voltage. This voltage is called the control variable of that dependent source. So V1 is the control variable, and mu is the voltage gain. Okay. The unit of mu is, well, it's unitless, or you can write volt by volt. Okay. So that's the first kind. Remaining three kinds, you can more or less guess. You're going to see voltage controlled current source, then current controlled voltage source, and finally current controlled current source. But the main idea is here in the first definition. Okay. 2 current controlled voltage source, CCVS. Okay. Now it's the same idea, but the control variable this time is current instead of voltage. Okay. I1, and here we have the source R I1, and here the voltage that it generates across its terminals equals R times I1. And I1 here is some current somewhere in this circuit. Somehow it communicates itself to this device, and this device produces that voltage R times I1. I1 is a control variable, which is a current, and R is called trans resistance. Okay, its unit is ohms. Third kind is voltage controlled current source. The control variable is voltage, and what's being generated is current. Okay. This time inside the diamond we have indicating that that's a dependent current source. G1. And this current equals G1. G1 is control variable, and G is called conductance, and its unit is moles or siemens. And finally, we have current control current source. Here, this is the control variable. Let's call it I1. It's a current, and here we have beta I1, and this current is beta I1. I1 is control current or control variable, and beta is the current gain. Okay, it's unitless, or it's unitless N over N. Okay, now this pictures may be a little bit confusing, but what we mean by that is the following. Let me quickly draw an example. This example circuit that contains a dependent source. Okay, circuits with dependent sources will look like the following. Suppose that we have a circuit here. Okay. This is an independent source. It's a circle independent current source. The current it provides is IST. Here we have an LTI capacitor with capacitance C. Here we have an LTI inductor with inductance L. And here we have a resistor LTI with resistance R. And then here we have a dependent source. Now, the picture is such that here we have plus minus, therefore this indicates that it's a dependent voltage source, and the voltage that it generates is R times its control current. Okay, it's a voltage source and its controller is the current, therefore it's a current control voltage source. Now the question is, what's I1? That information must also be given. And in this case, suppose that I1 is the current passing through our resistor. Okay? So what this component does is somehow it knows or it feels or it measures this current that is passing through this resistor, and what it does is across its terminals it generates voltage that equals this constant R times that current I1. Okay? And with other types you can also generate similar examples. Okay. Now the last component remaining for today is the ideal transformer. Let's also talk about them briefly, and once we encounter ideal transformer, we will remember its properties. Okay. This is our last component for today, ideal transformer. Okay. Sometimes we use the abbreviation IT. It's a K-branch component. Okay. A K-branch ideal transformer is shown by following. Representation. Here we have N1, N2, N3 up to Nk. These are the so-called turns ratios. This is the voltage of the first coil. Then we have V2I2, voltage of the second coil, and so on. And finally, we have for the last one, VK, IK, voltage and current of the kth coil. Okay. Now, that's how we draw it. Now the question is, what's the IV characteristic? Okay, how are the voltages and currents related to one another? The branch relations are as follows, or the IV characteristics. Okay. The voltages are related to one another as follows. V1 over N1 equals V2 over N2. N's are the turns ratios, and so all these ratios are equal to one another. Okay. So that's one set of equations that relates the voltages and where N sub J is the number of terms for the J branch. Remember that we have 1, 2 K branches. So that's one set of equations, associated voltages. Currents are also related to one another through the following part of the terminal equation. N1 I1 plus N2 I2 plus Nk Ik equals 0. Okay. Those two sets of equations together characterize and describe the K-branch ideal transform. Okay. Let's end the lecture by the following exercise. Here is a statement. The total power of an ideal transformer is defined by you sum all the powers of each branch. Okay, therefore I1 V1 plus I2 V2 plus I3 V3 and so on. J runs from 1 to k. Now it turns out that no matter under what circumstances you're operating that device, in what type of circuit, no matter what type of circuit that it's used, this sum, which is the total power of either transformer, is always 0. Okay. And it's not difficult, in fact it's quite a straightforward consequence of determinant equations. So therefore I leave that as an exercise. Exercise, prove this.